Okay, well, I'd like to say good evening to everyone. I'd like to welcome all ICMA members and guests this evening to our first technical lecture of the 21-22 season. It's my great honour and privilege to be given this opportunity to be president of the West Midlands branch, and some may say well overdue too. Before we commence with the main event, I would like to take a brief moment to congratulate Dave Hall on last year's presidency. Dave has set the bar very high for us with a selection of world-class presenters and diverse topics. And although he couldn't be with us tonight, I know full well that he will continue to be a great source of support and advice for myself. For most, I'm certain that the last 12 months has probably been one we would all rather forget. However, in very difficult and challenging circumstances, I do believe that Dave has pioneered access to the technical programme with online meetings, content and live streaming presenters to ensure that we continue to support our institute and industry. Making the meetings accessible to national members, non-members and various IT platforms or equipment can only be beneficial in attracting new and diverse potential members. I'd like to reassure everyone that we are doing everything we can to facilitate live meetings again in the near future at Wednesbury, and my programme has been biased towards assumptions that in the months leading up to Christmas we'll be able to meet again in person. I know full well that how important that is to most of our members, but keeping everyone safe is by far the most important consideration. We will also do our utmost to ensure that social events, dinners and the quiz are integral to our journey back to life as we knew it. I just hope that the buffet hasn't changed too much. I have been extremely lucky and privileged to meet so many associates, friends and colleagues across my 29 years, yes, 29 years service to our industry, many of which are here online this evening. This is my opportunity to give something back to the industry, and I really hope I can justify the trust imparted to me by the branch. Evenings like this absorb such an awful amount of time and effort and resource, and I would like to say a huge thank you in particular to Pam Morell and Richard Heath for supporting me this evening. Leading up to this evening, so many people have offered their support. I know for sure that I'll be asking my colleagues at Vanguard to help me out more than ever, so you can all look out tomorrow. So I'm going to remind everyone to keep their microphones off. And what we'll do, we'll allow Ray and Neil to present. And I'll ask anyone who has any questions to put them in the into the chat room. There's a little bubble on the top right hand of your screen. And if you have any questions, just log them in there, and then I'll try to cover as many of the questions as possible at the end. So I'm just going to introduce Ray and Neil with their bios. So Ray started in the industry, started working at Fasico Longacre Research Centre in 1976, working on binder development before joining Fordath as head of technical service for Foundry products. In 1986, he joined Boarding Chemicals as product manager for Alphaset. He then moved into sales and marketing of Boarding organisation, eventually becoming European business director. In 1993, Ray started Eurotek Foundry Products, along with colleagues Dale Crystal and Norman Higgs, as an independent UK binder manufacturer and supplier. He is responsible for sales and technical area of the business and has overseen worldwide growth of the business over a number of continents, with now 45 years experience. Neil is a technical sales engineer of FMS. He joined FMS in late 2019. Has extensive experience in foundry industry, working for companies such as Richards for many years, specifically in the technical solutions and technical sales area. He specialised in thermal and mechanical reclamation equipment. More recently, Neil spent several years working for a medium-sized dust extraction company and was responsible for sales and design of dust and fume extraction systems in the foundry sector. Neil joined FMS as technical sales engineer with general overview of assisting the sales team and ensuring that the technical details were correct for inquiries they received. So I think I've spoken more than enough. So now I will leave Ray and Neil to present their paper on furan no-bake technology. Over to you then, Ray.
Thank you. Well, first of all, tonight's presentation is a strange world we live because of COVID, but I would like to thank you for the opportunity you've given me to address this institute, because I think it's important that we maintain and support our institutes as we meet the challenges of the post-pandemic world. It's important as a foundry industry, we all pull together and we all get through this best we can. I know many foundries are busy, but the demands of our industry at the moment are unprecedented, and let's hope this is the start of better things. Okay, and the presentation is on moulding materials, essentially furan no-bake, the continuing story. And I want to touch initially on the history of the development of furan no-bake. It was introduced in 1960 with the formation of urea formaldehyde and furfural alcohol resins. They were offered a unique ability to generate high mechanical strength, which is a significant advantage over at that time in organic systems, such as sodium silicate. And their organic nature meant they could be mechanically reclaimed for the first time. They also gave improved casting finish, particularly in terms of definition over traditional green sand. And this led to their rapid worldwide acceptance and use. However, the addition rates in those days were typically 1.5% binder, and the catalysts in the region of 50–60% catalysts based on things like sulfuric acid. The 1970s and the 1980s saw the furan no-bake system become the largest selling group of foundries and binders worldwide. And it also saw the introduction of, for the first time, phenol formaldehyde, furfural alcohol binders, and the corresponding copolymers, which meant they could basically be launched into steel foundries. At this point, addition rates were falling, and typically binder levels were in the region of 1.2%. But during the 1970s, we saw the introduction of a urethane no-bake pioneered by Ashland Chemicals, often now referred to their trademark, Sept. It began to enter the market and was particularly excellent in terms of cold-making abilities and also for non-ferrous applications. And also its sister gas cube process, cold box. During the 1980s, we saw the entry of the market of alkaline phenolic for the first time, based on Bourne Chemicals' Alpha, a patented system that was truly unique initially. It offered the ability to eliminate sulfur dioxide whilst giving very high surface fit castings, and was particularly taken up by the steel groups. That classic example, but for everybody will know, is the William Cook Group, who are a very traditional alkaline phenolic binder foundry. This led many times to discussion in the 1980s of the demise of furan no-bake as a moulding system. And I should know that because I was actually product manager at Alpha at the time. By the 1980s, however, there was concerns being raised. Alkaline phenolic binders typically only mechanically reclaimed at 70–80% due to their inorganic nature, whereas furan operated at 85–90%. This has then been unpinned by further developments in the resin, reducing the binder levels down to 0.9 to 1.1% binder, and subsequently lower sulfur dioxide on emissions. The 1990s saw a huge step forward with the new development of a reactive furan binders like Eurotek's permacoal grade. Again, they're available UFAs, PFAs, and copolymers. But this dramatic advance meant we could, for the first time, bring binder levels down to levels such as 0.75 to 0.9%. Consequently, lower acid levels and sulfur emissions were reduced in the foundry by some 40%. The first time we saw the commercial use and development of what we call process control units. Many people know as temperature blenders, acid blenders, but this gives us the ability to control the acids against temperature and maintain a significantly lower sulfur dioxide emission. This meant many foundries, particularly ferrous foundries, looked to move away from alkaline phenolic back to furan because of the mixed sand cost saving. It also go lower sand waste disposal, and in the early 90s we're beginning to come back and for this, which accelerated the interest in sand reclamation, which furan is an ideal candidate for, because essentially it's organic in opposed to the inorganic properties of sodium silicate and alkaline phenolic. To be fair, PEPs also offers an organic ability to be thermally reclaimed. But due to its lower ability to mechanically reclaim, it often means thermal plants have to be significantly higher than you would expect with a furan system. And you can see on the graphs on the right-hand side, resin addition in the 1960s at 1.5, and we're going to discuss further addition rates as low as 0.6 by 2020. Sulfide dioxide emissions on first-time mixed sand have reduced from 0.16 to 0.04. Yeah, these are quite dramatic changes in a period of 30 to 40 years. The 2000s saw continued development, and again, it was the reactivity of the binders that has moved us forward. To the Envirocol range, for example, and other companies will manufacture very much more reactive binders. This has meant furan can now run between 0.6 and 0.75 for very well maintained sand systems. And again, it offers low mixed sand cost, improved overall sand reclamation, and reduces SO2 by a further 30%. And this shows the trend of the graphs opposite. This has also led to further advancements in process control, strongly introducing more accurate blending and remote access support to ensure chemical usage is minimised, which will be seen later in the IBS system marketed by Foundry Machinery and Spares. An example I personally give, most Saturday mornings I get a phone call from one of the biggest furan users we sell to from India, where he makes very large boxed and boxless molds at degrees of 50 degrees and requires some fine tuning on his blending. And we do this remote control very easily, very rapidly, and very successfully. He maintains addition rates of 0.7% binder on poor local quality sand and maintains ability to produce large molds at over 50 degrees centigrade, something that we would not have been able to do back into the 1970s, early 80s. Recent developments have seen the introduction of even higher performance polymer versions of furan novate. Why have we brought those in? Two reasons. One is to reduce the demand and the use of furfural alcohol in the binder. And the reason for that is very simply to drive costs down. I think there's probably nobody in the industry who doesn't know the impact at the moment of FA on furan binders worldwide with the COVID and the Chinese situation in export, with furan prices probably at the highest price they've been for 25 years. So it's something we need to look at, we need to work on, and it's something that's now been introduced into the market. This has also been driven as well by the fact we have new REACH environmental considerations, where free formaldehyde levels have to be less than 0.1% of the binder. And this we are now achieving on a readily acceptable basis. Going back to furans in the 90s and the early 2000s, they wouldn't have achieved this. They'd have been less than 0.5% free phenol or free formaldehyde, and therefore would have been outlawed on the new regulations. Furthermore, as I said, the ability to actually mix and control sand up to 50 degrees gives us a unique ability. And this is now being underpinned with the development of new lower sulfur catalysts, which for the first time are giving us the ability to achieve those goals and also maintain the performance and the strength. I mean, in the old days, the classic way was always to basically water the catalyst out, which is no good in terms of big molds at high temperatures because of the through-cure characteristics. So I'll just quickly discuss the three groups of chemicals. There's the traditional furan, which we call Permaset, the more reactive series, Permacol, and the new very reactive series, Envirocol. And you can see here, for example, in the early days, Permaset is a traditional furan binder, Permaset. It's used for large box moulding, it gives you good breakdown, but it is a traditional furan system. Permacol was the first step in the development of environmental friendly binders. It has high reactivity, low catalyst requirement, and low binder usage. And here's an example where you can see from a fast loop a mould being picked up after 6-7 minutes and moved to the coating station because of the high mechanical strength and the rapid set. And I think Alex Simmons will be quite happy, let me tell you, that's where it is. Okay, and then we look at the Enviroco. They're the spirit of the latest environmentally friendly technology. It offers low emissions in terms of SO2, free formaldehyde, free phenol, and also biological and chemical oxygen demands. A classic case at the moment of reclamation is, for example, an alkaline phenolic. If we analyse an alkaline phenolic, it has 3.5 to 5.5 milligrams per kilogram of elutable phenol. New furan is less than 0.02. And then the other concern in the industry at the moment is concentrated elutable carbon. Alkaline phenolics are in the region of 400 to 500 milligrams per litre. Furan is calculated at less than 2. So these are dramatically more environmentally friendly products than we think, particularly its ability to be able to go to waste. So let's look at some of the benefits. We have high core and mold strengths. This means we can typically turn the binder down dramatically from where it was at its early concept. We have excellent reclamation properties. We can reclaim 85 to 95% with mechanical alone. And the example I always say to foundries, if you do everything right with a furan mould, you'll get a good mould. If you make anything bad with a furan mould, you'll still probably get a good mould. Other processes such as alkaline phenolic, you won't get that. You have to do everything absolutely right to maintain the quality. It's an abusable system. It's high reactivity. It gives you fast set times. It's ideal for boxless moulding, fast loop systems. It has now lower acid concentrations and requirements. This lowers cost. It lowers sulfur dioxide. It has low viscosity now compared to what it used to do, which means you get much more better compaction and higher surface finish than you did with traditional furan binders 30 years ago. We offer low free formaldehyde, as we discussed, low free phenol content. And that meets the new REACH regulations, fundamentally very important. We're supported by automated acid blending. And it's operational between 5 to 50 degrees centigrade, which is a major change, what we've seen over the last 30 years. We have a technology now called air pure, which we'll go on to shortly. And that is a mist that we can spray during the casting to eliminate sulfur dioxide. It's not an odour, it's not a perfume, it's actually a reagent which is non-carcinogenic. We developed with Durham University, which is a material that converts SO2 to SO4 and removes the problem. Okay, there's a cost. Of course there's a cost. You're spraying an ingredient during casting into the atmosphere, which therefore has to meet all environmental requirements. It's non-carcinogenic, it's non-hazardous, it's non-flammable. It's essentially a benign product. So here we can see some typical examples of furan in action. And we look at some of the big excellent definition we get on these colours. We're looking at high mechanical strength. These are moulds being picked up off fast loop in about 6 minutes for coating. We have low fume now at the mixing station, albeit on an omega machine where there is an extraction point on it, I'll admit. But the level of free formaldehyde and free phenol and free FA on this system is dramatically lower than what we used to see 20, 30 years ago. We see high levels on this particular foundry of mechanical reclamation. They reclaim at 90 to 95%, although they do use a secondary attrition unit for the last 3 to 4% rather than the thermal. We see the improved mould definition because of the low viscosity. We see the ability, because they're generating mechanical strength, to be able to apply coatings quickly after the moulding process starts. We don't see the same degree of softening back of coatings that we used to see traditionally 20 years ago. This, for example, here is, this is people making large iron castings at 0.7, stripping them in 5-6 minutes. We see the use of chromite sand on the big cores opposite, and the very good improved breakdown because of low binder levels. So what we're trying to put together is a development package where we put the improved binders, which have low fume, with the control panels, the better control, the ability to remove sulfur dioxide, to meet REACH regulations, to have the ability to reduce costs because it's no longer having to be mass volumes like most processes going through the reclamation system. We can actually just dump 5% or even then introduce, if necessary, thermal reclamation. It's organic, it doesn't need additives, it works very, very well, very successfully, and there are many foundries worldwide thermally reclaiming. So that it gives you the ability to close that loop, but it still means you need to have a sensible control of your sand system, understanding of your sand system. It's not an excuse to just get away with poor practice. If you put good practice together with furan, you will make excellent molds of very low mixing cost. And here's an example why. And it's just generating, but essentially, if you look at it, you look at the mechanical strength of, for example, these are dog bones tests taken in PSI at 1 hour, 2 hour, 4 hours, and 24 hours. Standard furan will generate out about 155 PSI after 24 hours. Improved furan system now will generate over 225, a significant jump. That jump is seen more in the 1 hour strength, where, let's be fair, most of us are handling our molds. So from 50 to 60 PSI, we're now hitting levels of over 100. And that strength then can be traded by lowering the addition rate. We don't need it all, so we can then lower the addition rate, lower the cost, lower the chemicals going into the sand, improve the environment. So until recently, and the problems that have arisen with furan and furfural alcohol supply, you were suddenly offering a product that environmentally was better than previous, and it was actually cheaper, mixed sand costs. So it wasn't a difficult concept to sell. When we talk about the AeroPure, well, the AeroPure, as I say, it's a non-hazardous product which reacts with the sulfur dioxide, because let's be fair, it's the sulfur dioxide that's got the bad name. It's the elephant in the room as far as furan is concerned. And it gives us the ability to remove it and reduce it. Remove it, in terms of metallurgical issues, the sulfur reversion, and also SO2 issues in terms of the environment that people work in. And here's an example we did. And the top right-hand corner shows a really poorly controlled furan foundry, who after 6 minutes of casting were hitting short-term exposures of 12 parts per million, which is ridiculously high, probably 6 times the legal limit. The introduction of the aeronaut at that point rapidly put that product back under control and let it run at around 1 part per million within 10 minutes, which is a significant change for them. That said, if you look at the process first, get the better resins, the better acids, you won't be achieving the 12 parts per million. So the AeroPure is there is to complete the loop, not to offset poor practice, which many people think it is. It removes, I say, the SO2 from the casting area to SO4. So it's not, as we saw in the past, there used to be chemical reagents that smell like perfume. That's not very lovely, but still have all the SO2 inside them. These are actually removing SO2. It is non-hazardous, the reagent. It's benign. I'm told you can actually officially eat it, but I wouldn't recommend it. It's robust. The plant is very simple. You can see it's an automated spraying system. It's low maintenance. It's low cost. It's simple to install. It can be put in many places in the foundry. It can be put on timers. You're not talking massive cost, low operating costs. And also, as a side issue, the AeroPure, there's a version that actually works with TEA, which gets rid of the TEA aspect for a cold box. You can link it to SO2 monitors, which we've done successfully overseas, so people can monitor the SO2 in the Foundry and can have a log to show the health and safety executives when they turn up and request information. It's put in as a fine mist, and it's usually put on 5 minutes after casting, and then it runs for about 10-15 minutes, and then it's switched off. It's a unique droplet system formula that picks up a surface area and absorbs rapidly the SO2. Okay. Let's just then talk about process controls. These were launched in the 80s and 90s, and it gives, and Neil will come on and talk more about them, but they give consistent production. They reduce mold scrap. They reduce sand wastage. And that can be said, also be fair for the other processes they can work with. They reduce binder, but importantly, for furan, they reduce catalyst levels, which means we can now use the lowest sulfur containing catalysts. You can link them to flow control, data logging, so you can work out how much material you've used, and also now remote control. And the new level, which we brought in, is significantly better still. This has been pioneered very much by people such as FMS. And maybe Neil can maybe go on there to explain now.
Yeah, basically the two ways, you know, the original way of blending was manual. You had your set cure times and recipes within a control panel, and it was very manual. The operator had to select it. If the sand temperature gets higher, you needed more chemicals. If it got lower, you needed to adjust it further, and the calibration was key from an operator. Whereas when we developed this system with Eurotek, we looked at the differences of what was required and when it was required through the day. You know, these systems don't just go in the UK; they go all around the world, as Ray said, in India, for instance, where you could be getting up to 50 degrees, but at times it could be a bit lower than that. So the system uses a PLC control, typically a Mitsubishi or a Siemens based system. So it's an industry standard, if you like, and is constantly calculating what's required through the PLC control and the settings that are in there at commissioning, to ensure that the set times and the strip times that are required are constant through there. And that helps your production, it helps the quality, it just makes the life so simple for the operator. All he's really got to do is fill the box and away you go. It can be overridden, of course, if you want to change and extend the strip time or decrease the strip time by temperature offsets, and we can set those within the program as well. But it's also
Neil, another point that is critical, I think, is, you know, you can actually minimise the usage. For example, that is a screenshot of somebody in India last weekend who was running at 0.7, but next day they can turn that to 0.68 by punching a button. That automatically puts the acid immediately. You don't have to recalibrate it. So instead, yeah, we no longer got that, well, it's 0.7 whilst you're at 0.8. You know, you can go 0.7, 0.7, 0.7. You have the ability to control the chemicals as low as possible for your production.
Yeah, and it's instantaneous because they're all inverter driven as well, right?
Sorry.
Yeah, the system also, Carl will tell you the remote connection side of things. We've got a cloud-based system now that we pretty much put on a standard to all systems, which allows the chemical guys to be able to connect remotely. If there is some tweaks to do with the calibration, they can do it there and then. You can monitor the usage of all your materials to see how much you're using from a business point of view. You know how much sand's going through, you know how much chemicals you've used, you know how long you've been mixing for. The information that you can get off these systems now is second to none. There's no information that you would possibly need that you can't get, and it's straight away you're in there with the REMCON system.
Yep. Next page. Yeah.
Yeah.
I'll just touch on this. This is an example of what we talked about earlier with standard furan. If you look at the group, we look at the use of the blenders where we put a certain amount of fast acid, a slow acid, into the system, which is linked to temperature. So the first example is a typical old-fashioned furan system, where you see you're using probably up to nearly 60% fast acid at temperatures of 0 or 5 degrees on a really cold day. And many of the new acid blender when they first came out were just straight on. You know, when you put in 60% there, you got 0 there. You put 15 on there, you got 1 there. And we learned very quickly that was ridiculous. In certain chemical processes, it may work, but we have no doubt it doesn't work for furan. You need the ability in the equipment to bend this graph to be able to achieve what you wish. And you are typically not bringing slow catalyst into the equation until 15 degrees. And then most times above 40 degrees, you're looking to remove the fast catalyst. And again, that will depend on what catalyst you choose as fast and which catalyst you choose as slow and which resin system you start with. So then we looked at how can we improve it. When permacoal came out, we saw a change. The graph started to change dramatically. The highest point here started to drop. Okay, so we look at that and we say, okay, we can now run at 30 to 40%. We can bend that graph differently. We can get more performance to achieve what we want. And again, as we develop the chemical process of the resins and the acids, we've underpinned it with the support of the equipment manufacturers to give us the ability to control that. And again, we see here now with the latest systems, we probably typically run around about 35% compared to 60% in the early days. And we're pulling that graph different again. We're dropping fast acid out now at 30 degrees. And the slow acid has the ability to generate a through cure at even large molds at very high temperatures. And again, that's linked to the performance of the chemicals. And again, underpinned with an ability within the equipment, the way that has developed, supported. Neil?
Yeah. Are we swapping the sharing? Yeah.
Yeah. Yeah.
Yep, I've just made you the presenter, Neil, so share your screen and you should be good to go.
Okay. Are we seeing that, everyone?
Yeah.
Right. So moving on from Ray's brilliant points on reducing the chemical usage through the technical advances.
At the moment, Neil.
Let me try again.
You want me just to click through from my presentation, Neil? You tell me when.
You can do.
Yeah.
It is saying I'm sharing, but
Yeah, we can see
Yeah,
we can see your screen now, Neil.
right, brilliant. Obviously took a little bit of time to come through. So as I was saying, moving from Ray's points on the technical advances that he's made with the chemical systems themselves, over the years, thermal reclamation has been used with the furan system quite extensively, and I've been involved in many projects for it, and it's been brilliant. The main advantages of doing this is that it gives a more stable product in the long run, and it also eliminates, I think is the word, the need to dump the sand and be reliant on a good new sand addition coming in from the quarries. And it's getting to the stage now, and I was speaking with Pam and Richard from the CMF a while back, that it's getting harder and harder for people to dump that sand at a reasonable cost and a reasonable effect on the environment. So before I sort of go on to the results that you could typically get with that, for those that don't understand a thermal reclamation system, the sand has to be mechanically reclaimed, as you would be in most instances when using the furan base, and we take out the metallics in a cleaning tower, and feed it into a furnace, which is this area here, which is gas fired, and that can be natural gas or it can be propane gas. It doesn't really matter, and heat ignite the organic compound that's on the sand, which is easily ignited and burnt away to almost 100%. So in effect, what you're actually doing is creating new sand from sand that would have been sent to landfill or dumped in wherever you were putting it. So what happens with that is that during that process of combustion, the sand is maintained at about 710 degrees, and it will totally combust the organic compound. But not only that, it will eliminate the VOCs, which is a big issue when thermally reclaiming at low temperatures. If you reclaim at any lower than that figure, and many people have tried to do it, it doesn't give you a totally clean sand, and you will get very weak bonding unless you put lots of resin on it at the moulding side. So that's where we would need to be. So as I say, it's becoming a big concern to the industry on the dumping side of things. So at FMS, we're developing smaller and smaller throughputs of these systems. Typically, you'd been looking at 1 or 2 tons per hour minimum to be able to get a return on the investment of the equipment that you would need. So it's now becoming something that is achievable with even the smaller foundries, all the way down to 250 kilos per hour. That would still be a system that could work well. So when we look at thermal reclamation, what we're effectively doing is taking the loss on ignition away from the sand and creating a clean sand. So what I've done is I've put together a graph over a 12-month period with a company in the UK using the latest furan technology from Eurotek, so that you can see where it works and where the results are. And when it was first installed, the sand system, and this goes back to what Ray was saying about maintaining a good sand system and good housekeeping with it, was running somewhere in the region of 6%, which is very
non-ferrous.
Yes, it was a non-ferrous, but it's a big number, and requires more chemicals to create those molds, even when running on an 80-20 sand blend. It still needs a lot more chemical in there. So after about a month of being in, we first did it on the first day, should I say, and the red line at the bottom is the LOI of the clean sand, and that was running at 0.02%, sorry, which is indefinitely better than new sand that you would have purchased. The dust content was nice and low because it's classified at the end of the process and cooled back down to ambient temperature for reuse. And every month we took those readings, and as you can see, the blue line steadily decreases. So the overall sand system LOI over the 12-month period has dropped to below 3%, but the LOI of the reclaimed sand, which is introduced as the new sand edition instead of buying new sand and dumping, has stayed at a relatively constant. There are a few little peaks and troughs, but it was ranging from 0.02% to 0.04%. Again, very, very low in comparison to the new sand additions that you would typically buy from your regular suppliers. By doing it, it also reduces the cost of the resins that you need to be putting in, but it also reduces the costs of the overall sand cost, when you can take into consideration the purchase of new sand, the dumping of new sand, and the chemical additions that you need to be putting in there. And I've done various paybacks for various customers over the years, and you can pretty much reduce the whole process by about 60% per ton of sand on a daily basis. You know, you still have to buy some new sand, but if that was 10% of what you were dumping originally, that would be a high estimate. I think you'd agree with that, Ray?
Yeah, absolutely. I mean, the key is the reduced waste and.
Yeah, but it also reduces the chemical usage that you need as well. And not only that, certainly in this day and age, with lorry drivers being scarce, quarries not mining so much, I've known several customers in the UK complaining that they can't actually get sand and they're having to use reclaimed sand on everything, which is affecting their moulds, their production, their waste, their scrappage. So it puts you in control of the whole system by adding this on to the very latest furan technology that Ray's speaking about. Okay.
Yep.
And then just moving further forward, and I'm not going to go into too much detail of continuous mixers because I'm sure we've all been in the industry long enough to know what they are, but this is just the sort of range that we do. We do the traditional single arm mixers, which can be coupled together with the temperature blending technology and the sand gates, and you can have blends, single sands, chromite sands if you need various ways of blade configurations. But the main thing with any mixer is maintaining that shaft and blade for the mixing. Many people have looked at putting in resin mist or chemical mists and ways of spraying them in, providing your blades and your mixing trough is maintained. Then these don't offer much benefit to the finished product at all. And of course the range of articulated mixers, which are fairly standard around the world. There's the belt mixer and the screw mixer. Again, can be used with either manual technology or the automatic blending technology that we talked about earlier, and can range anywhere from 5 tons per hour to 60 to 80 tons per hour. Okay.
Yep.
And I'll pass you back for the final slide, Ray.
Yep. If you can let me the presenter again, please.
I'll stop sharing.
Yep, you're the presenter again, right?
Yeah, I was picking it up, mate. Okay, we've got through nails. Okay, we've got through nail slides you're just saying. So just as a summary, some foundries will always regard other no-base systems as the panacea for them, such as urethane and alkaline phenolic. Okay, that's the way it is. Because certainly with steel foundries, there's a big need or a big requirement to get very high quality surface finish. There's always a battle for many foundries of the mixed sand cost against the casting cost. And what is that casting cost? Is the savings to be made in surface finish and fettling costs. So there's always a balance. In real terms though, neither of the two broad processes have really changed in 30 years. There'll be claims by ourselves and other suppliers about our products are slightly different and everybody else's is different. But the reality is, yes, urethane have reduced the odours compared to what they were from the concept. But the basic chemistry has not changed in 30 years. It relies heavily on thermal sand reclamation, particularly for non-ferrous. This penalises, in many cases, small to medium-sized foundries. It's very good, for example, in some of the core making applications, where many of us have seen, we reduce hot tears by the introduction of urethane technology. So all these things have their niche, but the basic chemistry in 30 years has not overly all changed. Alkaline phenolic are the other biggest moulding group, and they're essentially unchanged in the 1980s. Most suppliers produce similar binders with very minor variations because the chemistry is the chemistry. Binder levels are typically 1.3 to 1.5 for a well-controlled foundry. For many poorly controlled foundries, are on at 1.7 and 1.8. And that's because of its inorganic nature. Mechanically, levels at 80% are the best you're going to do unless you start putting secondary attrition or thermal attrition into the equation, because the chemistry, being inorganic, is difficult to change. And the issue I raise here is you have to put an additive in for thermal reclamation, and you have to make sure that additive is mixed and introduced. Failure to do so will result in the thermal plant actually going solid. And it also, the other issue that you're doing in many situations, you have potassium buildup in alkali phenolic. And when you thermally reclaim it, you're trying to convert what they call elutable potassium into non-elutable potassium. So the more elutable potassium you have to increase your additive levels. And that takes very careful monitoring and control. But essentially, the mold strengths with alkaline phenolic are very similar to what they were in 1985. Meanwhile, furan, we've seen on this presentation, has changed dramatically in the last 50 years. With the latest range of binders such as Eurotek, Ltd and Eurotek Ltd making big change further. These binders then can be introduced with process control. They got the advantage of the air pure systems to get rid of the real negative in the room, which is the sulfur dioxide emission. The latest range of alcohol binders are also now less dependent on further alcohol, and they'll be seen more into the market over the next 3 to 6 months. Why? Because further alcohol is out of control. It's a very expensive product. But that said, even in these crazy, unstable times, furan offers in well-run foundries at least 15% saving in mixing costs and 20 to 25% in less controls. And when raw materials returns to some level of normality, the saving is in the region of 40% on mixed sand costs. So it's this balance of ways between mixed sand costs and casting performance and its overall casting finish, which the foundry has to look and has to consider. Are furan binders a universal answer as a sand binder? No, they're not. But they're probably the most likely to meet that demand. There always will be the niches. Like I said, in steel, there's some non-ferrous application where urethane gives a much better surface finish. But overall, furan will continue to be the largest selling foundry product group. It was predicted to be unsaleable and obsolete in 1980. Yeah, there they remain 50 years, 40 years later, as the biggest sellable group, and the developments will continue into the next decade, which unfortunately for some of the other processes won't happen. So that's the presentation, gentlemen. I really appreciate the time you've given us to present what we need to say. We appreciate your patience, and I think me and Neil will try our very best to answer any questions or queries that you have, and hopefully we can address them to your requirements. So we open the floor to any questions, please.
Thanks very much, Ray, and Neil. That was brilliant. Loads of pertinent sort of issues. Just speaking, from our own perspective at Vanguard, you raised a lot of pertinent issues there. We have got some questions in the chat room, so I'll just go through. I'll try and capture all of them if I can. The first one that came in was, have you used AI in remote recalibration of the mixer, taking into consideration changing temperature or humidity?
Okay, recalibrate. I'm not quite following the question. Okay. You said, have we have the ability to alter the calibration remotely?
It looks like
I think it probably talking about viscosity with the with temperature changes and humidity changes, Ray, maybe.
That certainly can be done with the introduction of flow meters. I mean, which is something that's been standard on a lot of mixers, like the IMF recirculating pump systems. So by connecting flow meters in UK, we have done that many times in the past. So these control units have the ability to do very much what you want them to do. In many cases, in certain temperature climates, maybe people don't see the value of that because it doesn't change quite so dramatically. Because these are very thin materials we're talking about. So unless it gets to exceptional cold circumstances, you're not going to see that variation. You would if on alkaline phenolic, I agree. They're much higher viscosity products. But certainly on the very high performing furan system, the viscosity are remarkably low and are not really affected by humidity at all.
Yeah. And with regards to the artificial intelligence, the PLC takes control of that, and it's only as good as the information that we're giving it. So a good quality flow meter, as Ray said, would give that information and allow it to throttle back the inverter on the pump to ensure that it was giving the or increase even to give that flow that was required anyway. So
and I sort of talk from personal experience of dealing with both of you guys. I know that if the Foundry wants something in particular, you can usually customize it as well, you know, depending on what the Foundry wants.
We have some of the control
technology. Yeah,
we have some of the control panels, for example. I know we have Mesa where they'll have, you know, the customers will have job numbers in there, photographs of the jobs in the screens, where the shields go, you know, where the sleeves go. So you can make these things almost do whatever you want them to do. You know, some people have, you know, spare part lists inside the panel itself. You know, so it's very much you can take it where you want to take it. The technology now, it's a bit like, you know, I always use the analogy of video recording. You know, 30 years ago, you press, you know, play, record, and stop. You know, now it'll do anything for you, and you're probably paying less money for it than you did 30 years ago. Technology has moved that far.
Yeah, and I think from an equipment supplier's point of view, we pride ourselves on having a standard product range that isn't standard, because no foundry works the same, operates the same, has the same requirements. So when we're out and about, we talk to you, we find out what you want, we put a proposal together based on you. It's bespoke for you, rather than it just being, right, you want a 5-ton mixer with an IBS, there you go, and we're out the door. We will back you to the hill and give you the solution that's right for you. So if you want to look at auto calibration, we can certainly look at that and build that in.
Okay, thank you. Hopefully that answers the question. We've got a question on thermal reclamation, but I think it's obviously specific to alkaline phenolics. With thermal reclaim, does it remove all the potassium? I'm new to the industry. That's a question in the chat room. So that you touched on the potassium.
Well, this is the problem, Carl. You get elutable potassium on the sand, which you need to convert to non-elutable, so it doesn't affect the rebonding strength of the sand. And that is what they put an additive, which is essentially a clay-based additive, to actually stop to make that happen. One of the problems you have with alkaline phenolic systems is, if the sand gets out of control even a little bit, it will increase that level of elutable potassium on the sand. So you have to then increase the additive as a percentage into the thermal plant to balance that. And it's understanding that and being able to respond on a regular basis. If you imagine, it's like taking a sand sample out your thermal plant every 2 hours, analysing it, and then deciding where to go next. And in many cases, people don't do that. They're in a situation where it's just a certain level going in all the time, which is okay as long as the sand is maintained at the mixing station. If it's not, and it creeps up, then you'll start to get the sand system get out of control. And what you can, many of us seen it where, you know, we've seen people throw the sand system away, because it's got worse and worse and lower quality. And what you also maybe have to remember is, on the alkaline phenolics, when you thermally reclaim them, they never come back to the same mechanical strength as actual normal sand. And we've only recently seen, you know, sand where people are reclaiming thermal and getting strengths 60% of what they would with a typical backgate or chopper sand, because the alcohol is built up in the system. Even though they've neutralised it, it has an impact on the rebound strength.
Yeah, and you also have the issue of going back to the additive system. You know, that is something that needs to be maintained by somebody who knows what they're doing as well, and regular checks, making sure that the additive's there, making sure there's no splits, making sure it's flowing, making sure it's working properly, because if it's not done, you will have a lot of expensive repairs to do to a thermal reclamation plant.
Great. Okay, thanks. A lot of detail there for everyone, but I've got a couple more questions to ask before we finish. One about, I guess, what's the sort of optimum ratio of reclaimed sand used in furan, and also then to Neil, what length of campaign for thermal units, typical running costs and return on investment?
Okay, do you want to go first, Ray?
Well, mechanically, you should be able to reclaim 95%. If you've got a sensible binding system, you run it 0.65, 0.7. There's no reason why you shouldn't, as long as you control it. I mean, you have to remember, you're going to lose probably 3% of your sand system anyway on castings and dust extraction. So you're never going to achieve the panacea of 100%. So to me, thermal reclamation closes the loop. What furan offers you is, what size thermal plant do you want? Do you want to buy a quarter of a ton an hour and get your foundry running, or do you want to buy, using, for example, alkali for light, and you buy a 2 ton an hour unit? And that's the differential you're looking at. But yeah, mechanically, when you rebond furan, strengths go up. It's organic. When you rebond, for example, alkali phenolic, it's inorganic. The strength goes down. It's a chemical thing you can't get away from. But you should certainly, in my opinion, no furan foundry should be looking at 85 to 90%. But it's about controlling the chemicals going in to maintain the lower loss of emissions, the lower sulfurs, and using the right catalyst and right resins.
Yeah. Going on to running costs, that obviously depends on the deals that you've got with the energy suppliers, but you normally in the region of 20 cubic meters per hour of gas per ton processed, and 20 kilowatts of electricity for a 1 ton plant. So it really depends as well, you know, return on investment, what your deal is with buying the new sand and dumping. But if anybody has a specific requirement that they'd like to look at and talk about, I can certainly put payback sheets together based on information that you give me on utility and sand figures. But I would expect for a 1 ton plant in an average foundry, you'd be looking 18 months to 2 years as a return on investment on a full thermal reclamation plant.
Okay, I'll make sure your phone's switched on in the morning.
It's always switched on. It's always switched on. 7 o'clock in the morning.
That was a 5% discount on it.
I've got one more question. Typical FA and the latest binders now in comparison to the more traditional binders?
Yeah. I mean, there are higher FA resins we're talking about now, and the biggest problem we all know is FA. Traditionally, FA would be, 20, 30, £1,000 a ton. You've got FA now in regions of £2,500 a ton because of a combination of market forces, lack of material coming out of China, COVID, all the other issues you've got. Because the problem you have essentially, you only have two main sources for alcohol, main sources, which is China and the Dominican Republic. So once China pushes their price high, the Dominican Republic tend to follow it. And that has been a big issue. Certainly from Eurotek's viewpoint, we're looking more and more to more polymerized resins, which means the need to put less further alcohol in. What we cannot do is trade strength performance and also acid demand performance. So therefore, it's been a combination saying, right, we've developed the resins quite dramatically. There's a lot more work we can do on the catalyst, so we can then balance back some of the reduction in further alcohol by changing the catalyst sulfur levels to give a system that's still acceptable for foundries and maintain some of the lowering of the cost. We don't see FA levels coming down, if I'm honest, for at least year end the way they're going, and could get worse. They will come down, no doubt. But it's a volatile market. But I think this year has been unprecedented on the basis we've seen alkaline for like resins at the highest price in many years. We've seen the problems getting MDI, which is a key part of the pets and cold boxes. Yeah, there's a world shortage of that. I think we've seen it with coatings, with isopropyl. I think we're all in very strange waters at the moment. But as a developer of things such as furan, we have to be aware of it and do what we can to try and offset this without trading the improved quality that we built over the last 20 years.
Thanks, Ray. I think from my perspective, I've been in the industry 29 years and worked in foundries, from the onset using furan, and I can honestly say, the development's been phenomenal. And every foundry I've worked with, it's been discussed of, furan's going to end. It's not the future, but I hope for everyone tonight, your presentation and with Neil's support has proven otherwise. At this point, I'd like to ask our colleague Mark Holliday to give his vote of thanks, please.
I'd like to say Ray Higgins from Eurotek. Thank you very much for the depth of experience that you've shown tonight. We all know sound systems are really complicated and we need to control them the best we can. And you and your colleague Neil come across with some experience and knowledge, which is something we all need to get under control of the current environmental restrictions we need to work to. So I'd like to put, on behalf of the West Midlands Birmingham Coventry Branch, I'd like to thank you in the normal way with a show of hands.
Cheers, Ben. Thank you. Cheers, Neil.
Thank you.
Thank you. Thank you.
Thanks, Mark, and thanks to everyone for attending tonight. It's another huge milestone, I think, for myself personally, but I'd like to thank everyone for supporting me, and I know you all will continue to do so in the weeks and months ahead. Just so everyone knows that if people want the copy of the presentation, we'll get. You can obviously contact Neil and Ray directly.
Absolutely.
I guess we can pick up email requests from the chat room. I think that would be possible, Richard. Anyone that's asked specifically for a copy.
Yeah, we can do that.
We can do that, no problem.
Yeah, and anybody that wants to contact us that hasn't got my details, certainly feel free to contact Richard or Pam or Carl, and they have my details. Pass them on freely.
Yeah, absolutely. We're here to help one industry.
Yeah.
So yeah, huge privilege for me. So thank you very much for all your effort and support and doing these presentations. It doesn't come light. I know everyone's busy. Everyone's got a hectic program, but it really does make a huge difference. And I think it, lifts the spirits when we can all get together this way.
I'll just say one thing though, Carl. You're a very hard man to say no to. Very hard.
No, I do appreciate your support. I really do.
Thank you for the time. Appreciate it.
Next month we've got a presentation from Coldries, and it's an application of refractories for melting and pouring. That one, I'm hoping that we can stream it live from Wednesbury. We will do our utmost to make that happen. Hacken will be based in Sweden, so I don't think he'll be travelling to the UK for it, but fingers crossed that we'll all be able to meet at Wednesbury in October. So really nothing more to say other than thanks for your support. Have a good evening, and I don't have to say travel safely, but make sure you're not late for work in the morning.